Hello, this is Robin de Graaf and welcome to another video on the basics of NMR. Today I would like to talk about signal processing. This is a video that follows another video on Fourier transformation. Before we go on with some more sophisticated features of spectral processing and signal processing, let's review some of the things we learned in the video on Fourier transformation. So in NMR, our signal is acquired in the form of a free induction decay, and that has the general form of a signal that starts with maximum intensity equal to M0, the thermal equilibrium magnetization, and it exponentially decays over time with T2 star relaxation, due to T2 star relaxation, and it oscillates at a certain frequency. The signal is mathematically described as such, where M0 is a scaling, we have a complex exponential with a frequency in it, and we have a regular exponential describing the T2 star relaxation. And these are again the three parameters. If we now do Fourier transformation, we basically take this signal and convert it into a frequency domain spectrum, in which now the frequencies are on the horizontal axis, and the intensity shows you if those frequencies are in the sample or not. So in this case, there is a frequency of about 8 Hz corresponding to the oscillation right over here. The magnetization M0 is basically the sum underneath this curve, and that can be deduced from the mathematical equation describing this signal. So time domain signal, Fourier transformation, you're going to get your frequency domain signal. It has a real component that is shown. It also has an imaginary component, and I'll talk about that in a few slides from now. So again, the M0 is now proportional to the area under the curve. The frequency can be read from the horizontal position, and the T2 star is equal to 1 divided by pi times the frequency width at half maximum. So all the three parameters that describe the FID also describe the spectrum. As I mentioned in the earlier video, Fourier transformation is reversible, again underlying the fact that the parameters in the time and the frequency domain are essentially the same. Now, unfortunately, the description so far is missing one parameter, one fourth parameter, and that is the so-called Nmr Signal Phase. So let's have the situation where we excite our magnetization from the z-axis, and we excite it perfectly along the y-axis, and then we start to acquire our free induction decay. In that case, one of the two axes, the signal is maximum, and in the other orthogonal axis, in gray here, it starts at 0. In this case, the phase is said to be 0 if we define the y-axis as 0 phase. Fourier the equation is given by the same one that I used on the previous slide, and we actually don't need the phase. However, there are many experimental conditions where the phase is not 0. In other words, where the magnetization isn't perfectly excited along the y-axis. It could end up somewhere else in the xy plane. In this case, it has a certain amount of phase, phi. If we now start to acquire the data, then you can see now the first point is not along the y or the x-axis, but it's somewhere in between. So both the black and the gray curve have some intensity. Mathematically, it is the same equation, except we add a complex exponential having the phase term in it. Note that there is no time dependence, unlike there, and that is because the phase remains the same for all times. So that's why it's just a time independent parameter. Now, what kind of effect does this phase have on the NMR spectrum? Well, if the phase is 0, we already know we do Fourier transformation and we're going to get a complex valued spectrum in which the real part in black is the Lorentzian line, and the imaginary part, which is typically not shown but it's always there, is an out of phase Lorentzian line. Now, what now if the phase is not 0? You can again see it on the FID. Both signals have some intensity. Fourier transformation of this, we're going to get a signal that looks something like this. The black spectrum has negative intensities and positive intensities. Clearly this is undesirable. In this situation, the area underneath the black curve was proportional to M0. Well, that is no longer the case here, right? You have negative signal, so this area is certainly not the same as that area. So that's undesirable. If we have multiple small peaks, it's much harder to recognize those little peaks in this scenario. So in general, having a non-zero phase is unavoidable, but it's also undesirable. So we need to do something about that. Well, in order to understand what we can do about it, we first need to understand its effects a little bit better. So let's have a look again at the time domain signal. Time domain signal ft has a real component to it, measured along one axis, plus I times the imaginary component, measured along the orthogonal axis. The entire equation looks like this. Again, the four parameters, m0, the frequency, t2 star, and now the phase as well. Take a complex valued FID, you do a Fourier transformation, you're going to get a complex valued NMR spectrum, in which you get a real spectrum, that's the one that is typically shown, plus I times an imaginary spectrum. Now, the real spectrum is given by this equation, in which A is the absorption Lorentzian line and D is the dispersion Lorentzian line. The equation of the absorption I've already shown earlier is given by this, and that corresponds to our desired signal, all positive intensities as narrow as possible. The dispersive component is given by this equation and corresponds to the one that we are not so interested in. Has very broad, long tails, has net zero intensity, is broad. So we always get that, but we want to make sure that this one is completely in the imaginary part of the spectrum, so we don't see it. And we want to make sure that the real part is equal to the absorption part. So if we look at this equation right here, we can make the real spectrum equal to the absorption spectrum if the cosine of the phase is equal to 1, which indeed is the case when the phase is 0 degrees. But of course now we have a situation where the phase is not 0. So what can we do about it to make it 0? Well, that is something that's called phase correction. This is our time domain signal. If we now multiply this with a phase correction term, if that phase correction term equals the phase of our NMR signal, the exponent actually cancels, and you're going to be left with an FID, a time domain signal, in which the phase is 0. Now, how to determine this phase correction? That can be done with automated algorithms, but very often you just do it iteratively, you do it manually. You're going to have some kind of sliding bar, and you're going to have your spectrum. Clearly the spectrum is not in phase, right? It has positive and negative intensities. So what you then do is you just start sliding the slider, and you can see that the peaks went up a little bit less negative, even better, even better, even better, and now we're perfect. You can see all the lines are up, they're positive, they're symmetrical, and so a phase correction of 50 degrees eliminates the dispersive component, and now the real spectrum, that's the one that you're looking at, equals the absorption spectrum. Now this so-called global or zero order phase correction is a standard like procedure in NMR data processing. There's nothing wrong with it. You will always have a scenario where the phase will be not 0, so you have to just correct it this way. There are other phases that are much more undesirable, and they should be eliminated within the experiment. One of those phases is a so-called linear phase or first order phase. Suppose that we have 3 different chemicals, 3 different set of spins, each with its own frequency. They are excited along the y-axis, and if we start acquiring the signal at time is 0, of course each of them evolves at their own frequency, but they all start at the same point along the y-axis. So Fourier transformation of this spectrum gives us 3 signals, and they're all up and in phase. But if for some reason now we have to delay the acquisition a little bit, let's say that we excite our magnetization in a transverse plane, but we're not able to start acquisition immediately. There's a small delay, delta t. Well, the spins are initially excited along the y-axis, but during that delay delta t, they will acquire a phase given by this equation. And this will show you that the phase for a constant delay delta t is linearly proportional to the frequency. So you can see that after a certain amount of time t, delta t, different spins have acquired different phases. If we then start signal acquisition and we do Fourier transformation, we're going to get a spectrum in which each peak, each line has a different phase. It is clear that this is not, you're not able to phase correct it as we did earlier, because if we get the red peak in phase, the blue peak and the green peak will not be in phase. Now, you can correct this with the so-called linear or first order phase correction. I would generally recommend against it, because it can lead to baseline oscillations, and it's better to design the experiment in such a way that you don't have a delayed acquisition. Okay, so that's all I wanted to say about phasing. The next thing is, so far we have assumed that we had a continuous analog signal. But of course, modern NMR works with computers, so we need to convert this analog signal to a digital signal. Then the question becomes, how rapidly do I need to sample the analog signal in order to get a proper digital representation? Well, that is governed again by the same equation, where the phase is proportional to frequency and the sampling time. And because the phase is only defined from minus pi to plus pi, that defines the maximum frequency that can be sampled accurately. That's a so-called Nyquist frequency, and it is equal to 1 divided by 2 times the sampling frequency. So let's have a little bit closer look. If we zoom in here, and we digitize this analog signal in gray, we digitize it by sampling it at equidistant times delta t, which is our sampling interval. That's also called the dwell time. Clearly the frequency of this signal is smaller than 1 divided by 2 times the dwell time. You can see that this period is much larger. So one period there are multiple samples, and therefore upon Fourier transformation the signal appears in the spectrum at the proper frequency, the true frequency. You can see that the spectral width is given by 2 times the Nyquist frequency, and the spectral width is also equal to 1 divided by the dwell time. So in this case everything is good. What now if we have a signal with a much higher frequency? The dwell time is the same, so we sample it with the black points, but now you can see that the real frequency, which is the gray line, is not sampled twice per period. It is actually sampled less than twice per period, and therefore it violates the Nyquist sampling frequency. However, the sampling points still make up a frequency. If you connect the dots between then you get an apparent frequency at a lower frequency. And that's exactly what happens. If the true frequency here is at 4.5 kilohertz, the peak will actually appear at minus half a kilohertz. It basically folds back, or it aliases back, because it violates the sampling frequency. Now the frequency at which the peak appears is easy to calculate. It is the real frequency minus the spectral width. Now this is generally undesirable. First of all, let's say that we observe a peak here, we might assign it to a certain chemical or to a certain compound, and that's of course incorrect because it's not at its true frequency. In another case, when this peak falls right on top of another peak that was already at that frequency, then we cannot separate the two. So those are two problems. Another potential problem is if you have noise outside the spectral width, that noise also falls into the spectrum, therefore lowering your signal to noise, and that's a big problem. So let's say that we have a spectrum with 2 lines in it, and the spectrum is very sparse, right? So we want to reduce the spectral width, let's say like tenfold. Well, in that case, the noise here and the noise here is going to be aliasing into the spectrum. And so if we reduce the spectral width tenfold, you can see that our noise is much higher. In fact, the signal to noise is square root of 10 lower than what it was over here. You can also see that one of the two signals is also aliased into the NMR spectrum as well. Well, clearly the decrease in signal to noise is a big problem. In NMR we're often signal to noise limited, so we certainly do not want to give up signal to noise this easily. The solution to that is to apply a so-called audio filter. In an audio filter, you basically have intensity of 1 across the spectral width and 0 intensity elsewhere. That means that you multiply the noise with 0 and you multiply the spectrum with 1. If you now reduce the spectral width, it's basically only the zeros that are folding in, and that doesn't matter. So therefore, reducing the spectral width now maintains the signal to noise at what it was originally. Also notice that the signal that was outside the spectral width, which was aliasing in here, is now being removed completely, right? Because the digital filter, the audio filter, has suppressed it. So this could be a problem. If you expect a spectrum with 2 signals in it and you only observe 1, you might be very much confused, or it may even lead to an incorrect conclusion. One thing to notice also is that these filters are not applied in the frequency domain. They are typically applied in the time domain, but the effect is as shown here for the frequency domain. A lot of viewers may be more familiar with MRI, and these effects can also be observed in MRI as well. Let's say we have an image sampled over the full field of view. This is the frequency encoding direction, and this is the phase encoding direction. For those of you who are not familiar with these terms, they will be discussed in a future lecture. If we now reduce the field of view in the frequency encoding dimension, that is the directly sampled dimension, then the audio filter suppresses signals there, and you're just going to get a smaller image in which you don't see the edges of the brain here. So there is no signal aliasing because of the filter. If you do the same thing in the phase encoding direction, the phase encoding is an indirectly sampled dimension. Therefore, the signal that was here is folding over to the front, and the signal that was on the front folds back to the back of the brain. And so there is signal aliasing. Now, this is a problem because now you cannot distinguish signal that was originally there plus the signal that came from the other location. You're just going to get the sum. So in this case, you need to use some form of like parallel imaging to disentangle the two magnetizations. And this will be discussed in a lecture on MRI in the future. So far we've been talking about the discrete, the Fourier transformation as applied to a continuous signal, where we have also an integral over a continuous signal. But now we have this discrete digital signal. So now the integral now needs to be replaced by a summation, and it's now called a discrete Fourier transformation. Main problem with calculating the Fourier transformation this way is it takes a lot of calculations on a computer. That's why in 1965, Cooley and Tuckey, they described the so-called fast Fourier transformation, which through a combination of recursion, they basically made the discrete Fourier transformation and make it into smaller and smaller packages, and they can calculate it much faster. So the number of calculations that you need is given by this equation. If you run some typical numbers for a one-dimensional FID of 256 points, the fast Fourier transformation is really 32 times faster than the discrete Fourier transformation. For an image, it'll be already a factor of 1000. Now, in the original paper, it was shown that the FFT is fastest when n is a power of 2, and that's why you still up to today you still have matrix sizes of 128, 256, or 2048, because those are multiples, those are powers of 2. However, on modern computers, FFT is almost as fast for powers of 3 or powers of 5 and other numbers as well. So it's not too much of a consideration, but these matrix sizes of a power of 2 are still available, present today. So the final thing I would like to quickly talk about is something that you can do now that the signal is in the digital domain. You can do some additional operations to the signal. One of them is so-called time domain filtering, or apodization. Let's say that we have a phosphorus FID signal here, and upon Fourier transformation that gives us an NMR spectrum with phosphocreatine and ATP, with a signal to noise and a certain line width. If we now apply a decaying exponential to this free induction decay, then we suppress the noise at the end, leading to an improved signal to noise. But of course at the same time the signal decay is also faster, leading to a shorter apparent T2 star and therefore to broader, wider line widths. We can also do the opposite, where we multiply it with an upgoing exponential. The noise at the end is now emphasized, leading to a lower signal to noise, but the apparent T2 star relaxation has increased, leading to narrower lines. This operation here is typically referred to as line broadening, and of course it is not the line broadening that you're interested in, right? It is the associated improve in signal to noise that is the goal. Now, you also have something that's called the Lorentzian to Gaussian transformation, and the goal of that is to improve one of the two without affecting the other too much. This is all based on the fact that a Gaussian line, if they have identical areas and identical line widths, a Gaussian peak is higher and has a narrower base. Now this fact you can use to come up with a weighting function that in this case keeps the resolution the same but improves the signal to noise. You can also modify the parameters slightly, and now the signal to noise stays the same, but the resolution is improved. Of course, what should be emphasized is that these are all like cosmetic changes, right? The fundamental underlying data, the free induction decay, hasn't really changed. It's still important to do these operations because sometimes you can emphasize certain features in a spectrum this way, but they ultimately are cosmetic changes. The final thing I would like to talk about is zerofilling. So let's say that we have a continuous free induction decay over 64 milliseconds. Fourier transformation gives us a spectrum like this. Now, of course, we are in the digital domain, so instead of having a continuous signal, it needs to be digitized. In this case, we digitize 256 points over 64 milliseconds. Fourier transformation, digital Fourier transformation, gives us this spectrum. It doesn't look quite the same, even though we have satisfied the Nyquist sampling frequency completely. If we now overlay this spectrum over the analog spectrum, you can see that the digital spectrum does adequately represent the true spectrum. So what is going on here? Why does this one look so different from this one, even though everything seems to be okay? Well, it has to do with we have not sampled enough data points. If we look at this area over here, we can see that the dwell time, the time between two sampling points, is 250 microseconds, making the spectral width 4 kHz. We have acquired 256 points. If we do Fourier transformation of 256 points, we're also going to get 256 points in the frequency domain spectrum. So that will be 4000 Hz, 256 points, or 15.6 Hz per point. So going from that point to that point as 15.6 Hertz. Now, if the spectral features are narrower than that, as is the case here, you may miss some of the spectral features. Now, the obvious thing to do would be to extend the number of data points, because if you have more points here, you're going to have more points in the spectrum, and then you can describe the features better. But acquiring more experimental data will mostly be noise, right? At the end, the signal will have decay because of T2 relaxation, and there will be mostly noise, leading to a degradation in your signal to noise. The smarter way is just to acquire the signal as you have, and then just adding zeros at the end. Fourier transformation now gives you more data points in the spectrum. In this case, you would have 4000 divided by 1024 points, or slightly under 4 Hz per point. And now you can see that all the features that were in the analog spectrum are now also in the digital spectrum as well. Now, zerofilling may feel a little bit magical to some users, but of course we have to realize that we haven't changed anything to the data. Well, we have just added some zeros to the data, and so all we have achieved is visualize the data that was already there, but we didn't have enough data point for to actually show in the spectrum. But we haven't added any new information. So in summary, Fourier transformation is a flexible tool to analyze complex valued signals in a time or frequency domain, and you can go back and forth. If you have an exponentially damped sinusoid, it will lead to a Lorentzian frequency domain signal. If you have non-zero phase in the time domain, you're going to get a mixture of absorption and dispersive component in the frequency domain. The dispersive component is undesirable and can be eliminated through phase correction, either automated or iteratively manually. Discrete time domain sampling is governed by the Nyquist sampling theory, and if you violate that, you're going to get signal aliasing. Finally, you can do a lot of things with a digital signal once it's in the computer. You can phase adjust it, you can time domain filter it, you can zero fill it, but you have to realize that most of these operations are like cosmetic operations. Sometimes they're very important, but they're not essential. So a few exercises for those who are interested. If you want to contact me, this is how I look like. You can also shoot me an email. You can visit the website that is under construction right now. And many of the things I talked about can also be found in the 3rd edition of this book. I hope that you've enjoyed this video and that you will visit my YouTube channel in the future to watch some other videos.